I will set up a virtual environment and install PyTorch, Torchvision, Matplotlib, and Jupyter. I have prepared a Jupyter notebook to demonstrate PyTorch's datasets and data loaders. Import NumPy as NP, Torch for PyTorch, and Matplotlib PyPlot as PLT. Matplotlib is for displaying images. We'll use Torchvision's datasets to see example images from the MNIST dataset. MNIST stands for Modified National Institute of Standards and Technology. It is a large collection of handwritten digits. From Torchvision, import datasets to load MNIST. The root argument is to specify where we want data to be stored. Train equals true means we are loading training data. Download equals true means we download data if not already available in the root folder. The first time you run this, it will download the data and store it in the data folder. After the download is over, we can confirm MNIST data files are stored under data/mnist/raw folder. The length of the training data is 60,000, meaning it contains 60,000 image and label pairs. Let's look at the first pair. The pair contains a PIL image object and a label. The image size is 28 × 28, and mode equals L means it's a single channel image. The label value is 5. We can split the pair into image and label variables, and take a look at the image, like so. The image shows 5, as per the label indicates. The size of the image can be accessed with the size property of the image object. It shows the size is 28 × 28, as expected. Since the image has a single channel only, we use the grayscale color map to display the image using Matplotlib. We can convert the image object to a NumPy array and check the shape, data type, and minimum and maximum values. Again, the image size is 28 × 28. The data type is unsigned 8 integer, which ranges from 0 to 255. In other words, the color intensity is an integer value, ranging from 0 to 255, where 0 means no color, and 255 indicates the highest intensity level. To access an intensity value, we specify the row and column positions. We use a zero-based index to specify those positions. Let's pick an intensity value from the 7th row and 11th column. So, we say image NP 6,10. It returns 94. We can convert the NumPy array to a PyTorch tensor using the fromNumPy function. The tensor shape property indicates that it's a 2D tensor of size 28 by 28. We can display the tensor using Matplotlib. It shows the same number 5 as expected. Once we convert images into PyTorch tensors, we can use them with PyTorch functions and modules. However, converting each image as we have done so far would be too tedious. Thankfully, Torchvision provides a way to transform images into tensors more easily. From Torchvision, we import transforms, which has the toTensor function. We specify that to the transform argument when loading MNIST dataset. toTensor function will be used to convert images to tensors internally. Now, if we print the first image's type, it is a torch tensor. Let's also confirm the image shape and data type. Here, we see something different than before. In PyTorch, images are 3D tensors where the first dimension is the channel, which is the channel first format. Another thing is that the data type is float32, where the intensity value ranges from 0 to 1. For example, let's find the intensity value for the 7th row and 11th column. There is only one channel, so we specify image 0, 6, 10. It returns 0.3686, which we can calculate using the integer intensity value from the NumPy array divided by 255, the maximum intensity value. The value returned has extra decimal numbers, which we can round off to get the same value as the torch tensor gives. So, the toTensor function not only converts values into PyTorch tensors but also normalizes values, dividing the integer intensity by 255. Matplotlib expects a 2D tensor when there is only one channel, so we need to convert the 3D tensor to a 2D tensor. We use the squeeze function to eliminate the redundant dimension to convert the 3D tensor to 2D. The shape of the tensor returned by the squeeze function shows 28 by 28, which is a 2D tensor. We can use Matplotlib to see the 2D tensor in grayscale. We load the MNIST test data with train equals false. Even though we specify download equals true, it does not download as the test data was already downloaded into the data folder when we loaded the train data. The number of items in the test dataset is 10,000. Let's check the image object type, image shape, and label value using the first item in the test data. As expected, the image object is a PyTorch tensor as we specified the transform argument to the transforms to tensor function. The shape is 1 times 28 times 28, which is also as expected having one channel in the channel first format. The image label is 7, which we can confirm by using Matplotlib to display the image. Here, again, we use the squeeze function to eliminate the redundant channel dimension. Fashion MNIST is another image dataset from Zalando's article images. We load training and test datasets. As you can see, Torchvision's datasets provide us with a consistent way to load datasets and transform them into tensors. We set the train argument to true for the training dataset and false for the test dataset. The download equals true will download datasets once and save them in the folder specified by the root argument. As before, we set the transform argument to transforms to tensor function. You can print the training data object to see the summary information, like so. We can check the image object type, image shape, and label as before. The tensor has one channel only. No surprise here. We use Matplotlib to show the image. Again, we call the squeeze function to eliminate the channel dimension. The image is an ankle boot. You might wonder how I know it. Well, we need to check the label map to look up the label number to find the object class name. There are 10 classes like t-shirt, trouser, pullover, and so on. All fashion items from the magazine articles. The next dataset is CFAR10. It contains RGB color images. 50,000 training images and 10,000 test images. There are 10 classes, each with an equal number of images. We can load CFAR10 training and test datasets just like before, thanks to the Torchvision's consistent interface. The numbers of items in training and test datasets are as expected, 50,000 and 10,000, respectively. The image object type, image shape, and label are in the same format as before. However, the channel dimension now has 3 channels which are RGB channels. Matplotlib expects the color channel to be the last. So, we need to convert the 3D tensor from channel first to channel last format. We can use the permute function to swap the dimensions. We call image permute 1, 2, 0, which moves the first channel to the last. 0 here means the first channel since we are using zero-based indexing. The shape of permuted tensor shows 32 by 32 by 3, having the channel dimension at the end. The image label says 6. Let's show the image using Matplotlib. Can you guess what it is? We need to check the label map to find what label 6 corresponds to. Well, it's a frog. The image is pixelated and hard to see what it is. Let's display images on a smaller scale and also put the class name on top of each image. Again, I'm using Matplotlib to do that. Here, I'm iterating through images and labels, passing an index one at a time, and building a grid of images with 3 rows and 6 columns. It's a bit tedious to iterate through images and labels in this way. Thankfully, PyTorch provides the data loader class that we can use to iterate through datasets in a much simpler way. From Torch Utils Data Import Data Loader.
I'm setting the seed value to fix the random sequence for reproducibility.
Then, I create a data loader object, passing the training dataset, with batch size equals 16 and shuffle equals true.
Batch size equals 16 means that for each iteration, the data loader returns 16 image and label pairs.
Shuffle equals true means the data is shuffled so that each batch has random samples from the dataset.
After we iterate over all batches, the data is shuffled again. Any data loader is iterable, and we can make it an iterator with the iter function.
Calling next on an iterator returns the next element, in this case, the first batch of 16 images and 16 labels.
I'm printing the shape of the image and label batches.
The image batch shape shows a 4D tensor where the first dimension is the image index and the remaining dimensions are for 3D tensors, which are RGB images in channel first format. The label batch shape shows a 1D tensor where each element is a label value. So, if I take the first image in the image batch and check the shape, it shows the 3D tensor of the first RGB image.
Printing the label batch shows all 16 label values. We can also see the first label value, which shows a 0D tensor. It's a scalar value but still a tensor object. By calling the item function, we can get a Python native scalar value. Let's show the first image.
We specify image index 0 to take the first image from the image batch and permute the 3D tensor dimensions to move from channel first to channel last format. We also take the first label and convert it to Python native scalar value.
Then, use the label map to convert the label number to a class name. Finally, use matplotlib to show the image and the class name. So, the randomly sampled first image is a cat.
Let's use a for loop to iterate through batches of images and labels. Torchvision also provides a utility function to create a grid of images.
From Torchvision utils import make_grid.
For images, labels in train data loader, create an image grid with 2 rows and 8 columns, and convert images from channel first to channel last. I put a break so that it only shows the first batch of images and print labels.
This session ends here.
I hope you enjoy it and understand how the datasets and data loaders work.
Bye for now.